6.2, multiplying and dividing radical expressions. Properties of radicals is what we're going to talk about first, and we have to review our exponent properties in order to do this section. So let's get started. All right, in order to multiply and divide radicals, you must understand their properties and remember your exponent properties from before. So recall, if you multiplied x squared times x, that would give you x to the third power because the rule was that you added your exponents. And remember that if it doesn't have an exponent, it's an understood 1. So 2 plus 1 is 3. That's why it is x to the third power. And again, if you needed to write those out, that would be x, x, and then times another x. So that would be a total of 3. Okay? All right, so remember when you're multiplying variables with exponents, you add your exponents. When you are dividing your variables with exponents, you subtract them. Okay, think about multiplying and addition, both are getting bigger, whereas dividing and subtraction, both are getting smaller. So in this particular case, x to the fifth power y squared divided by xy cubed simplifies to x to the fourth because it's 5 minus an understood 1. So 5 minus 1 is 4. Remember, the number lands where the biggest number is to begin with. And then x2 and y3 subtracting, remember you subtract and it lands where the biggest one is. So that would put the y1 on the bottom. Okay? And we can't have negative exponents, so remember when you're subtracting, it'd be 2 minus 3, and if it's a negative it goes in the bottom because negatives mean we have fractions. Alright, so properties of radicals. Any nth root of a times the nth root of b, when you multiply, as long as your index is the same, you will get the nth root of the radicands multiplied together, which would be AB. Okay? So the main thing is you must remember to multiply, you must have the same index or you can't do it. And when we're dividing, if you have the nth root of A divided by B, you can rewrite that as the nth root of A divided by the nth root of B. And you can go back and forth between these. If you have a problem written in this format and you see that it's easier to do it this way, you can write it back and forth. It's the same thing. Okay, so go back and forth and use it to the best of your ability and work it out so that you can make it easier to work. All right, so note these properties that I just talked about, this property right here and this property right here, only apply to multiplication and division. This is not true for addition and subtraction. We'll do that in the next video. That's totally different. Just like your fractions, 1/2 and 1/4, you know how they're very, very picky. Same thing with any addition or subtraction. So just know we'll have to be looking at that later. But multiplication, just about anything except for, in this case, we have to have the same index. All right, so recall, we simplified in the last video the cube root of 54 x to the fifth power. And what you're looking for is a cube root that can come out of this. Or if you need to, you can always make a tree and do your prime factorizations. Well, 2 will go into 54 27 times, and then 3 will go into 27, and then 3 and 3. Once you have all your prime factors, you look for, in this case, we need groups of 3. So I need to have a group of 3, and I do. I have a group of 3 3s. So that would come out. And then this leftover 2 would stay inside the radical. So it would be radical cubed, radical 2. All right, and then you split up your variables. Okay, if I have x to the fifth, that's x, 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 and x. And because we're looking at cube roots, we need groups of 3, so I need a pair of 3's, and one pair of 3's comes out. And that leaves me with 2 left over that must stay inside the radical. Okay, so if you need to split them up so that you can see them in circle pairs of letters, or any which way you need to do it, just do it. You'll see me looking for perfect cubes. I noticed that when I saw 54, I knew immediately that that was 27 times 2. 27 is a perfect cube. It is the cube root of 27 is 3. So when I do it, I'm looking for those kind of things to make shortcuts. So that's how I easily became able to see it should be 3x cube root of 2x squared. But if you need to do the tree form, do that. We can multiply radicals when they have the same index, like so. This is the square root of 5x times the square root of 3y. And you just multiply the outsides. Now outsides we don't have anything but a 1, so that would just be 1. But on the inside I have a 5 times a 3, which makes the 15. And then the x times the y, which makes xy. And if it needs to be simplified, you have to do that afterwards. But in this case, this one is as simple as it can get. Okay, but most of ours are going to have to be simplified. And that'll be the name of the game from here to the end of the school year is simplify. We will simplify and simplify and simplify again. All right. Now, some of these get a little bit more complicated. Square root of 72x cubed y squared times the square root of 10xy cubed. Again, you multiply the outsides, and in this case we don't have any numbers outside, so that's 1 times 1, okay? But if you had a number, you would multiply the outsides times the outsides, and then you would multiply the insides times the insides, okay? So that would be 72 times 10, which is going to be 720. X3 times x, remember it's a 1 right there, that would be a total of x4 right here. And then y2 times y3 make a total of y5, okay? So this combined now is this total. And then you can tell this one has to be simplified because we have a huge number and we have 4 x's and 5 y's, so you know they can be split up. And remember, if there's no index, it's assumed to be a 2. This is a square root. So I look and see if there's any perfect squares that can come out of 720, and I know that 36 times 20 will make 720, and 36 is a perfect square. I grouped my other perfect square with that so that it was easier to see what would be left over. So I put my x4 right here because both of these are perfect squares. And then my leftover stuff, 20, and then the y5, because it's not exactly a perfect square, I put those together. So that way I can work with those in a minute. But if you look, the next step, 36x4, you can easily take the square root of that and make that 6x squared. Does everybody see that? It goes straight from that to 6x squared. And then 20y5, I split that up. I know that there's a perfect square of 4 comes out of 20. 4 times 5 is 20, and 4 is a perfect square. And then I took the y5 and split them up so that I have a perfect square here and leftovers here, just like I did before. So I'll look at this now and I'll say, okay, this is a perfect square, and so is this. That becomes 2y squared. Now, if they both are perfect squares, you must multiply these two together, okay, as your final step. And then my leftover is square root of 5y. That cannot be broken down any further, so I just tag it along. All right, so then the last step is just to multiply the 2 that came out as perfect. 6 times 2 is 12. x2 and y2 just put together, x2, y2, and then times square root of 5y. And that is your answer. And that one's done. Okay, again, if you need to use a tree and break that down, you can do that. That would be 2 and, let's see, what would that be? 3, 360. Split that up, that'll be 2 and 180. Split that up, it'll be 2 and 90. Split that up, that'll be 2 and 45. Split that up, that would be 3 and 15. Split that up, that would be 3 and 5. And now I've got all my prime numbers. And then I go and find pairs because my index is a assumed 2. So I need pairs. So I have a pair of 3s, pair of 2s, another pair of 2s. Whoops, I'm going off my board here. 2s. And you must multiply each pair of these together. So it'll be 2 times 2 times 3, and then with the leftover of 5 inside. So that 2 times 2 is 4, 4 times 3 is 12. And then you split up your letters. All right, looking at my letters, I ended up with x4, so I know that became x2. y5, I know 5 divided by 2, that'll give me 2 with 1 left over. Okay? So remember, when you're doing your exponents, you're dividing. So it's 5 divided by 2, which gives you 2 full sets and then 1 left over. Okay? And like I said, if you need to do it this way, you can, or you can look for the perfect squares and break it down this way. Either way, you'll get the same answer if you completely break it down. All right, next example says 3 times the square root of 10 times, because remember there's no plus or minus in between there, we know that means it's multiplication, 4 times the square root of 6. You multiply your outside numbers, 3 times 4, which is 12. And then multiply the inside numbers, 10 times 6, which is 60. Well, you know that's got to be broken down because that's too big of a number. It's not simplified. So I broke it down by 4 times 15. Square root of 4 is 2. That comes out. And then you multiply the outsides, 12 and 2 is 24. 15 doesn't break down. Now, if you needed to, you could make your tree again. That'll be 2 and 30, 3 and 10, and 2 and 5. And I only have a pair of 2s that go outside, and then the leftovers, 3 and 5, are multiplied together to give you 15. Okay, and there was already a 12 out there to begin with, so that makes 24 square roots of 15. Now you can check your answers. When you're finished, the only thing you can't really check this way is by the variables, and you can just count those. But if you take 24 and 24 times 15, you should get your answer when you multiply all this together. Okay, you can check your answers up here. 12 times 12 times 5 should give you 720. So you can go back and check your answers, and with your calculator. If you wanted to put all this in your calculator, you'll get a decimal, and then check your answer to see if that's the same decimal. But you've got to be careful because it needs to be simplified, and if it's not, you'll get the same decimal. It just won't be simplified, and it still will be wrong. So just watch that. All right. Now, division's a little bit more picky. You have to watch what you're doing. Division of radicals, you must recall that you can switch from the nth root of a divided by b to the nth root of a divided by the nth root of b. You can switch them back and forth. But remember, in order to simplify a radical expression, there must not be radicals in the denominator. Okay, that's bad. It's like against the law. We can't have that. All right, so we have to do what's called rationalize the denominator. And that means we have to rewrite the expression so that there's no radicals in the denominator, and then there's no fractions under that radical sign. Okay, so it has to be completely cleaned up. So on our first example, we have the square root of 16x to the 5th power y to the 7th power divided by the square root of 25xy. Now the first thing I noticed, 16 is a perfect square and so is 25. So that made me feel like it would be easier to see if I rewrote it so it's all under the radical in one big fraction form. See that? Going from breaking it apart to putting it together, which is opposite of what we did up here. You can go back and forth from this. If that helps you, do that, because then you can simplify your exponents and everything from here. All right, so looking at my exponents, I have an x5 and an x to the 1 power, and y7 and y1. So when you divide with your exponents, you subtract them. So that's where you get 5 minus 1, which is x4, and 7 minus 1, which is y6. Okay? So all I've done is simplified my exponents. Now I'm going to look at these and I'm going to say, well, what's the square root of 16? Well, that's 4. What's the square root of 25? That's 5. What's the square root of x to the 4th power? That's x squared. And what's the square root of y to the 6th power? That's y3. The radical is completely gone because everything became a perfect square. Sometimes that happens, and sometimes you have to go a little bit further and still have to simplify. But if you can see those patterns, it may help you to switch it so that they're all underneath one radical sign. Okay? This next example, however, is not that way. It's the square root of 5 divided by the square root of x. Well, we know now that we can't have this radical thing on the bottom of a fraction in the denominator. But we have learned already this year that undoing square roots we can do by squaring, and vice versa. They undo each other. So if I want to get rid of this radical, I need to square it. Okay, in order to square it, I would multiply by the square root of x again, because this square root and this square root are going to undo each other. Okay, so when you do that, whatever you do to the bottom, you must do to the top. So notice how I've got the square root of x over the square root of x. That's just making 1. That doesn't change my problem, which is the whole point. We're doing something so that we can manipulate those numbers so we can work with them. And multiplying by 1 will not change the original problem. So by multiplying by the square root of x over the square root of x, or 1, I can change this now to square root of x times the square root of x just becomes x. So I've gotten rid of that square root in the denominator. That's awesome. That's what we want to do. And then you just simply multiply the top. Well, what's the square root of 5 times the square root of x? And we just learned you just multiply the insides, and that's the square root of 5x. It's okay to have a square root on the top. It's just against the law to have one on the bottom. So this answer is simplified. Now, let me warn you, you cannot simplify these two x's because one is inside a radical and one is not. They do not cancel. They do not simplify. This is the final answer. So please do not do that. Anything inside any kind of grouping symbol, you cannot just cut them out with one that's not in a grouping symbol. These must be left alone. Now, if I had another square root and we could cut those out, that would be great, but that's not what we've got. This is the final answer. And this is fine. This is in the right format. We don't have fractions under the radical, and we don't have a radical in the denominator, so this is all good. So just remember, squaring will undo the square roots. So that goal is to undo those radicals that are in the denominator in whatever fashion we need to do. If it happens to be a 4th root, we're going to have to undo it with raising it to the 4th power. So whatever is going on in that index is going to determine what we have to do to that bottom. Okay? All right, and the last example, I believe, is the cube root of 4x to the 4th power divided by the cube root of 32yz cubed. Okay? On this one, we have a cube root in the bottom we can't have. We need to look at this, and we can look at this one a couple ways. In this problem, we have to make sure that everything, in order to undo it, is cubes. So we have to find perfect cubes in the denominator. All right, so I know that a couple things that multiply to give you 32, one of which is 8 times 4. And I like 8 because 8 I know is a perfect cube of 2. So I'm on to something right there. So if I look at that, then I can try to fix this with cubes. So I can split these up. But now notice I have just a y to the 1 power, okay? I need cubes in order to undo it. And everything has to have a cube in order to work. It can't just be one thing. It has to all have cubes. So what would I need to make y into y cubed? I would need to multiply by y squared. Okay, so we're going to need to multiply by y squared on the bottom, and z cubed is already a cube. That's all good. All right, so now I have a cube right here, but this has to be a cube also. Okay, I can multiply this 4 by 2, and that'll become 8 also. So you see, every single thing, all the parts underneath have to be in this cube fashion, or it will not undo this cube root sign. All right, so if I multiply everything by the cube root of 2y squared, that would be top and bottom, then that should undo all of my cube root problem on the bottom. All right, so that's what I did down here. I wrote the problem over. I multiplied by the cube root of 2y squared. So you see what happens is it'll be 32 times 2, which is 64. So I'll go ahead and write this out. Cube root of 64, y to the third power, z to the third power. Okay? So the cube root of 64 is 4. Y cubed will just become y. Z cubed will just become z. So now on the bottom, you know, it's all taken care of. There's no problem. You just simply, on the top then, multiply the two. You have the same index, so you can multiply them. So that becomes, on the top, cube root of 8x4 y2. Well, the cube root of 8 is 2. I can take a group of 3 x's out. 1 stays in. And then I can take, that's a y2. I don't have a group of those to come out, so that just has to stay inside. So this becomes this over top of my bottom. And that is almost simplified. You notice that I've got a 2 and a 4 out here on the outside. Anytime you have that, you can really technically simplify that too. Those are just plain numbers, so that would be 1/2, right? 2/4 is the same as 1/2, so I could just end up being x cube root x y2 over 2yz. Okay, so this actually simplifies to 1, and this simplifies to 2. Okay, so this would be, whoops, let's undo that. This would be my simplest final answer. Okay? Now, I know it looks like a lot of stuff, but the nice thing is we will be practicing in class on these. It just takes a little bit of time. Each one is going to be a little different. I wish I could say that they're all going to be the same, but they're not. They're going to have different situations for each one. So we're just going to take one at a time, and we'll do problems until we get really good at it. Practice makes perfect, so that's what we're going to do with this unit. I think, yeah, that is all for this time. So definitely come see me if you have questions. We will practice and get this straight. I'm available every morning. Just come in and see me, and we'll work on these on the board. Until then, see you next time.